So for today, we're going to go through the do now that's going to review the ideal gas law. So I want you guys to read through these two do now questions, pause the video, work through these questions with your groups on your do now sheets, and then come back to the video and check your answers.
So we're going to go through do now question number 1. And just to review, the do now question for number 1 was find the amount in moles of gas that occupies 60.82 liters at 31 degrees Celsius and 367 millimeters of mercury. So what I've done is I've actually gone through and I've labeled all the variables either that we're trying to find or that we were given. Now before I even figure out what equation to use, I noticed that I have one temperature that's in degrees Celsius. Now I need to convert that to Kelvin by adding 273. And so 31 plus 273 is 304 Kelvin. So I've now converted my temperature to Kelvin. So all of my units are what I need them to be. Volume in liters, temperature in Kelvin, and pressure can be in either millimeters mercury or ATM. Now, I'm only given one scenario here. I'm not given two sets of conditions. I'm only given one set of conditions, which means I can use the ideal gas law. I can use PV equals nRT. Because I'm solving for N, I have V, TP. I always am given R because that's on my equation sheet. So if I'm solving for N, I'm going to rearrange the equation. I need N by itself, so I need to get rid of RT. It's going to be PV over RT. And then what I can do is I can plug in my numbers. So 367 millimeters mercury, 60.82 liters. R, if I'm using millimeters mercury, is 62.36 times temperature, which is 304. So remember, I have just one set of parentheses on the bottom because otherwise my calculator is going to do order of operations differently. So when I actually am putting this in my calculator, I did 367 times 60.82, and then I did divided by, and I'm going to do 62.36 times 304 in one set of parentheses, and that's going to give me my answer. So my answer is 1.18. So N equals 1.18 moles of gas, and I don't know what gas it is, so all I'm going to do is say 1.18 moles. So in do now question 2, it says at what temperature in degrees Celsius will 0.888 moles of CO gas occupy 11.8 liters at 889 torr? So like question 1, I'm only given one set of conditions, which means I'm going to use the ideal gas law, PV equals nRT. Now in this, I'm trying to solve for T, so I need to get T on a side by itself, so I'm going to do PV over nR equals T. Now I'm going to double check, make sure all my units are where they need to be. N is moles, V is liters, pressure is torr. Remember, torr and millimeters mercury are the same, which means I'm going to use 62.36 as my value of R. So I'm going to go ahead and plug everything in. So pressure is 889 torr times a volume of 11.8 liters divided by N, which is 0.888, times R, 62.36. Now, I know I didn't put any of my units in here, which may not be the best thing to do, but I'm just trying to save some space here. What you do need to remember is what your units of R represent. So you have liters times torr over moles times Kelvin. So when you actually solve in this problem, your temperature is going to be in Kelvin. So when I solve for T, it's going to be 189.4 Kelvin. Be careful with units. Now the question though wants temperature in degrees Celsius. So remember, K equals C plus 273. So my K is 189.4. C is what I'm trying to find. So what I can do is just subtract 273 from my answer, and I get a temperature equal to negative 83.6 degrees Celsius. So that is my temperature in degrees Celsius. Remember that Fahrenheit and Celsius, which we don't use Fahrenheit, so Celsius can be negative, Kelvin cannot.
So the agenda for today, in class today, I want you to do the following in order. So I want you to start by taking the practice quiz. So this practice quiz was actually supposed to be a real quiz, but I wasn't going to give you a quiz while I was gone. So this is going to be a practice quiz on the simple gas laws. So I recommend trying it on your own so you know what you need to go back and review. Remember, it's just practice, but the link to this practice quiz is in the calendar that I sent you, and the answer key is on there as well. So you can work through if you want to grab a mark marker and just work through the problems on your desk, you can, and then go ahead and open the answer key and check answers. Then I want you to actually come back to this video and watch the examples on partial pressure and the discussion on it. So there's just a short discussion that reviews Dalton's law of partial pressures, and then I go through one example in your notes. Then I want you to do Dalton's law of partial pressures practice, which is pages 7 and 8 in the practice packet. So I want you to go through, work through it with your groups. The answers are on the website, so go ahead and check your answers. They're also linked in that calendar. And then if you have time, start the molar volume pre-lab. And so when I get back, we're actually going to do the molar volume lab. So I want you guys to be working through the pre-lab. Now the pre-lab is going to be purpose, procedure, pre-lab questions. So purpose, procedure, like normal. There is a video that's linked on the calendar, and it's also on the website. If you click on Unit 3 under lab, there's a video that I actually work through the pre-lab questions for you. So watch the video as you go through the pre-lab questions. And then just keep in mind that you have mastering that's due on November 14th. So I want to start by just reviewing Dalton's law of partial pressures and mole fractions. So if you have two gases that don't react and they're combined in a container, they're going to act independently. So if you have like oxygen and argon that are getting mixed in a container, those aren't going to react. Oxygen gas is not going to react with a noble gas. And so they're going to act independently. And so what that means is you can actually use the ideal gas law to figure out each individual pressure. Then the total pressure of the mixture of gases is going to just equal each individual one added up. Now, another way that we can find partial pressure is using what's called the mole fraction. And the mole fraction is exactly what it sounds like. It's essentially the fraction of moles in a container. So if you have oxygen and argon mixed together, you have 5 moles and 5 moles. Your total moles is 10. You have 5 moles of oxygen, so 5 divided by 10 is 0.5. What you can do is you can actually take the mole fraction and you can multiply it by the total pressure. So it's almost like a percentage. You can multiply the mole fraction by the total pressure to get the partial pressure of each. So if you know there's 4 moles of oxygen mixed with 6 moles of argon, it's 40% oxygen, 60% argon. That means that the total pressure, 40% of that will be oxygen, 60% of that will be argon. So what I want to do now is go through an example that is in the notes that actually looks at when you mix oxygen and methane in a container. I want you to calculate partial pressure and total pressure in the container.
So we're going to work through this Dalton's law of partial pressure example that talks about oxygen and methane being placed into a container. It wants to know what the partial pressure of each gas is, as well as the total pressure in the vessel. So something to keep in mind is when you put in two gases like oxygen and methane that coexist, they act independently. So when the 6 grams of O2 goes in, it's going to have its own pressure, and when this 9 grams of methane goes in, it's going to have its own pressure. And so what we can actually do is we can use the ideal gas law to figure out what the pressure of each individual gas is, and then to find the total pressure, we can actually add them together. So I'm going to start with oxygen. So we have 6 grams of oxygen. Now, in order to use the ideal gas law, we need to make sure that we have all of the correct units. So we need pressure, which we're trying to solve for. Volume is already in liters. N, so I'm going to have to figure out how many moles this is. R we always have, and temperature, 0 degrees Celsius, is 273 Kelvin. So what I'm going to do over here is I'm going to figure out how many moles 6 grams of O2 gas is. Now, notice it's oxygen gas, which is O2, and so the molar mass of O2 is 32 grams. So I'm going to do 6 divided by 32, and that's going to give me 0.1875 moles. So what I can do now in the ideal gas law is, remember, I'm solving for pressure. So it's going to be moles, which is 0.1875, times R. I'm just going to use 0.08206. That way I'm solving in ATM. My temperature is 273 Kelvin, and my value of V is 15 liters. Again, it's not the best habit to not be using units. I'm just trying to save some space. So 0.1875 times 0.08206 times 273 divided by 15 gives me a partial pressure of oxygen of 0.280, and because I used 0.08206, it's going to be an ATM. So here's the partial pressure of oxygen. Now I'm going to do the same thing for methane. So for CH4, I'm going to be solving for pressure, so I'm going to do N times R times T over V. Over here to the side, I'm going to do 9 grams, and the molar mass is 16 grams for every 1 mole. So 9 divided by 16 is 0.5625 moles of CH4 gas. So now I can plug everything in. So 0.5625 moles times 0.08206 times temperature of 273 Kelvin, all divided by the volume of 15 liters. And again, the reason that we can do this is because we act like when these two gases go into the container that they're independent of each other, and so we're looking at the pressure that they would exert if the other weren't there. So now I'm going to do 0.5625 times 0.08206 times 273 divide by 15, and for the partial pressure of methane we get 0.840 ATM. So there's the partial pressure of each of my gases. Now to get P total, I just add the two up. So I can do 0.840 plus 0.280, and we get 1.12 ATM. So you can actually use the ideal gas law to find individual volumes, or individual pressures, and then you can actually add those together to get your total pressure.